Soil shear failure happens in seconds. Without warning, gravity overcomes the internal friction of the Earth. Thousands of pounds of raw dirt collapse inward and instantly burying anything in its path. To control this hazard, we first have to classify the work. An excavation is any manual or mechanical removal of earth. A trench, however, is a specific geometric cavity, an underground excavation that is deeper than it is wide, capped at a maximum width of 4.5 meters. The professional mistake is treating a trench simply as an earth-moving task. Removing ground means removing structural support. Earth naturally wants to close an empty void. Creating a compliant trench means constructing a temporary, highly volatile structural engineering project, heavily reliant on rigorous spatial risk management. To safely open the ground, we have to build a multi-layered matrix of defenses. We will construct a compliant excavation site from the ground up by stacking 4 critical zones of protection. A trench exists in a state of constant tension. Ignoring even a single layer of this multi-hazard matrix turns a workspace into a site for a potential cave-in. This 3D block illustrates our first layer of defense, mapping invisible infrastructure beneath the surface. We cannot dig until we know what we might hit. Before physical work begins, a pre-planning phase activates. Engineers review the permit to work and piping drawings. Then, a surveyor physically scans the ground to verify blueprints against reality. The technology used depends entirely on the soil. Ground-penetrating radar emits highly accurate radar waves to detect pipes, but struggles in wet or salty earth. In those environments, surveyors rely on acoustic locators or electromagnetic tools to track buried cables. Mapping establishes hard operational boundaries. When a hydrocarbon pipeline is identified, standard machinery is strictly locked out. No mechanical excavation is permitted within 5 meters of these volatile lines. A secondary exclusion zone applies to live electrical services and non-hydrocarbon pipelines, freezing mechanical digging within 3 meters. To safely expose these sensitive utilities, crews must rely exclusively on the pilot trench protocol. A pilot trench requires workers to manually dig by hand. It is limited to careful 1.2-meter depth steps. Continuous physical verification and scanning are required before proceeding deeper. Striking an active, pressurized line in a volatile hydrocarbon environment instantly triggers an uncontrolled immediate fire or a catastrophic toxic gas release. Once utilities are cleared, operational focus shifts to the physical properties of the earth. Stability is measured by a precise metric, unconfined compressive strength. Soil strength falls into 3 categories. Type A soil is cohesive earth, like dense clay, capable of withstanding 1.5 tons per square foot or more. In this cross-section, Type A soil strength permits steep geometry, cut back at a 53-degree angle for a 0.75 to 1 ratio. It is also cohesive enough for benching, carving the earth into rigid horizontal steps to prevent collapse. Type B soil drops in cohesion. Composed of silt or angular gravel, its compressive strength sits between 0.5 and 1.5 tons per square foot. Because Type B is weaker, the geometry must adapt. The slope relaxes to a wider 45-degree angle, establishing a strict 1-to-1 horizontal to vertical ratio. Type C soil is highly volatile. This includes granular, non-cohesive materials like sand or submerged earth, with a compressive strength of less than 0.5 tons. To prevent this loose material from sliding, the trench geometry is pushed out to an extreme, shallow 34-degree angle, a 1.5 to 1 ratio. At this level of instability, enching is strictly prohibited. The soil cannot hold a vertical face, making shear failure nearly guaranteed if steps are cut into it. This creates an industrial spatial dilemma. Digging a deep trench in Type C soil requires massive horizontal space to accommodate a 34-degree slope. Complex, heavily developed sites rarely have that physical footprint. The engineered workaround for this space constraint relies on mechanical solutions. Crews use hydraulic shoring or steel trench shields to physically brace the vertical walls, counteracting the massive inward pressure of the earth. Sloping, benching, and shoring are not operational preferences. They are exact mathematical requirements dictated entirely by the compressive weakness of the earth. With the walls structurally secured, the primary hazard shifts inward into the empty void of the trench itself. As this depth gauge shows, crossing the 1.2-meter threshold legally and operationally reclassifies the excavation. It is now a confined space. Deep excavations alter atmospheric dynamics. Because the pressure at the bottom is higher than at the surface, breathable oxygen is physically forced out of the cavity, creating severe oxygen deficiency. This density trap invites toxic gases like hydrogen sulfide to pool at the bottom. In areas with limestone, carbon dioxide releases directly into the workspace. Mitigating these invisible hazards demands strict operational controls. Atmosphere requires continuous gas testing, forced mechanical ventilation to cycle the air, and a dedicated hole watcher stationed at the surface. Egress geometry is just as regulated. Secure ladders must be positioned every 7.5 meters along the entire length of the trench. Those ladders must extend at least 1 meter above the trench edge, guaranteeing workers have immediate, secure footing during a rapid evacuation. Without precise atmospheric monitoring and rapid egress points, the empty space of a deep trench acts as a highly efficient asphyxiation trap. The final layer of the safety matrix addresses the chaotic environment surrounding the excavation edge. The greatest threat from the surface is surcharge loading. Every ton of excavated dirt placed near the edge exerts massive downward pressure on the soil below, easily triggering a catastrophic wall collapse. In this top-down view, the primary surface rule is established. Excavated spoil must be kept 1 meter from the edge. Because heavy equipment introduces massive surcharge loads and vibrations, vehicles must maintain a strict clearance of 2 to 3 meters from the boundary. The perimeter requires physical reinforcement as well. Hard barricades at least 1.2 meters tall protect personnel from falling, while engineered bund walls block surface flooding from pouring into the trench. Surface work is further complicated by mobile machinery. Heavy excavators operate with massive momentum and carry severe blind spots. To control the movement of heavy plant, sites implement a strict banksman protocol. A dedicated spotter maintains continuous, two-way communication with the machine operator. The workflow is absolute. Ground workers cannot approach an excavator without explicit prior consent from the operator, relayed through the banksman. Pedestrian traffic across the site is limited to designated crossing points. Workers rely on engineered gangways fitted with tow boards and guardrails, measuring exactly 0.46 meters wide for safe passage. Surface geometry mathematically constrains the operational chaos. If the perimeter is ignored, the lethal blow doesn't come from below, it comes from above. Looking at this master 3D view, the compliant excavation site functions in perfect synchronized equilibrium. It is an exact chain of dependencies. A failure in utility mapping, a miscalculation in shoring geometry, or a lapse in atmospheric testing instantly collapses the entire safety matrix. This heavily engineered state is not permanent. It is inherently temporary and highly volatile. Environmental triggers can reset the math without warning. A sudden rainstorm, heavy vibrations from nearby traffic, or unexpected water seepage rapidly degrade the unconfined compressive strength of the walls. This dictates the final administrative control. A competent person must inspect the entire system daily and perform a mandatory reinspection immediately following any weather event or hazard exposure. Excavation safety is never a static checklist. It is a continuous, active resistance against the Earth's natural drive to crush the empty space.